Yeah, thank you for that introduction. All right, can everyone hear me properly? Wonderful. Yeah, thanks again for the introduction. I'm going to talk about sort of the latest counterfactual learning to rank. In particular, this talk is based on a recent TOIS paper. So this is a TOIS paper from February. So, and the reason I chose this paper is quite long. It's about 30 pages, but it gives a very good overview of the previous state of the art and the current state of the art. In particular, what I want to do for this talk, so I'll show the slide at the end again, if you're still interested in the paper by then. If I do my job rightly, hopefully so. What I'm going to start with is I'm going to give a general overview of counterfactual estimation as we see it, let's say, outside of learning to rank, in order to contrast it with what happens inside of counterfactual learning to rank, because this work is really about what the difference between those two were and how they've been bridged. So I made my job a little hard because now I have to basically introduce two of these things at once. So let's get started. So I'll start with a very simple setting that has nothing to do with ranking, so that then later we can compare it with a ranking setting. So that's single item recommendation. So the most basic thing that you can think of, right? We have a setting, it's basically a bandit setting. At each time step, we can take a single action. An action is recommending a single item, whatever that is, if that's a video, a product, or a web page, doesn't really matter. And our goal is to maximize the total number of user interactions that we get with our recommendations. So we want to recommend the items that the users are going to interact with most likely. And importantly, for now, I'm just recommending one item at a time. We do that based on interaction data that's logged from a production system. So I already have a recommender system running. That's where I get the data from. So the real question here is, can we evaluate or optimize a new policy, so a new recommendation system, based on data that's gathered by a different system? So I have data from one system, and I would like to evaluate a different system. So basically, without doing any sort of putting a system into deployment, can I already tell how good it is from what a different system has done? So I'll visualize that like this, right? So here on the left, we have our interaction data. In this case, it's one interaction with item B. And on the right, we have our recommendation policy. That's a probability distribution over the different items. And the most straightforward or naive way of doing things is simply saying, well, the user interacted with item B, so B must be a good item. So I'm going to look at, in my policy, how likely was my policy to recommend this item. I'm basically saying, well, if the user interacted with B, if my policy is also likely to recommend B, that must be a good thing. If it's not, that must be a bad thing. So we can do this direct match. Now, if you know anything about off-policy reinforcement learning or counterfactual estimation, you can maybe guess why we call this naive. It's basically because what I've been ignoring here is that the picture is not complete. In fact, the way I should think about it is that actually I've completely ignored here where the data is coming from. In actuality, there was a logging policy. There was a system already running. That system decided that B was going to be shown to this user. Then we saw the interaction. And then I was going to match that with my own policy. But if I ignore that this data came from this logging policy all the way on the left, it's going to affect my evaluation. And that's not what I want, obviously. So to put that in formal terms, what I want to estimate is the expected reward. So if I have a policy pi, I'd like to know in expectation, so X here is just some context. And then I'm going to sum over all the actions. So here we have the actions A. And then I have the probability of this item being recommended under my policy, and then the probability of an interaction with the item. So the right here, you could see it as sort of the relevance or the quality of an item, right? So this is what I would like to, this is the value I'd like to know. This is what I want to estimate. But what the naive estimator does is basically says, well, we don't know that probability of an interaction. So I'm just going to put my observed interaction in there. So the interaction in this case, let's just assume that it's a binary variable. You can do this with other things as well. And at the face of this, this looks pretty close, right? It looks like if we take the expectation here, we're going to end up with the same, with that value, right? The expected value should match. But actually, if you do it, the logging policy probability enters the equation. Because basically, in this equation over here, we are not summing over all the actions. We're taking the action that was chosen by the logging policy. So what's happening is that the logging policy selects which data points we see, and thereby gives more weight or less weight to items in expectation. So this is a typical form of selection bias. Basically, we will have to correct for this if we want to make sure that our expected values line up and that we have an unbiased estimator. If you know anything about selection bias, then you probably also heard about inverse propensity scoring. So this is usually the method that people talk about for correcting these things. The idea is very simple. It's basically you can reweight your observations to counteract the selection bias under, well, most of the time. There are, of course, specific conditions. So in this case, we have the inverse propensities here are basically 1 divided by the probabilities of the logging policy. So it's not a probability distribution, but if you multiply the logging policy probability with the inverse propensity for each item, you end up with 1, basically. So you end up with a uniform distribution. Another way to think about it is we know that item B is very much overrepresented, right? The logging policy gives it a high probability. That means in the inverse propensity, it's going to get a very low weight. Because we know it's overrepresented, we're giving it a low weight to counteract that. Vice versa, item C here is very much underrepresented. So we give it a very large weight to compensate that the other direction. So the basic idea here is by making this, instead of linking the interaction now directly with the new policy, we multiply it with the inverse propensity first. So this is inverse propensity scoring. Probably if you know anything about selection bias, you've seen this before. The difference between the naive estimators now that we use the ratio between the recommended probabilities. So here we have the IPS ratio. On top, we have the new policy, the policy that I want to evaluate. At the bottom, we have the logging policy, which is the policy that gathered the data, that has enforced some selection bias on the data. And if you calculate the expectation here, we do get the thing that we want to estimate. So it's unbiased because our expected values are is correct. And what I've basically done here is we're dividing away that probability that enters the equation in the previous case. Not all is good. The downside of this approach is that if this probability up here is very small, if the logging probability is very small, we're giving a very large weight to a single observation. That basically means we're amplifying the noise, which gives you a lot of variance. So this is unbiased, but it can come with a lot of variance that you don't want either. So there are other methods of dealing with selection bias. The next one I want to talk about is the direct method. So in the direct method, you assume that you have some form of regression, something to estimate your reward. In this case, that's the interaction probability. But the direct method doesn't care about where that comes from or what that is. So I'm visualizing it here with the magic wand. That's just to indicate, as far as the direct method is concerned, it could be anything. So we see it sort of as an oracle or like magic. So it's going to give us an estimate for each of the items. So these are not actual interactions. These are predicted interaction probabilities. And because we have one for each item, we can match them with each of the items in the new policy. So we don't have selection bias, right? We've solved the problem of selection bias. We have a value for each of the items. Unfortunately, though, the values are based on our regression model and not on actual interactions. So we've solved the selection bias problem, but now we're sort of all in on our regression model being correct. If I put that in formal notation, this is basically the expected reward, but now we replace the actual probability that we don't know with a predicted probability. So we've solved the selection bias problem, but if our regression models or regression estimates are not correct, we still have a bias problem. So we now need all these probabilities to be predicted 100% accurately. In practice, that's never going to happen. It basically means that you've already solved the problem before you apply this method. So in practice, you can expect this to be biased. However, you have zero variance from interactions. because they are completely ignored, right? Nothing in this equation is affected by the interactions, so we have no variance from the interactions. So this is kind of the other extreme, where we've completely solved the variance problem, but now we're stuck with a bias problem. So now I'm ready to talk about the method I really want to talk about, which is doubly robust estimation. The idea of doubly robust estimation is that we're going to combine the best of both worlds. And the key insight, the way to think about doubly robust estimation is you could use IPS to correct for the error of your direct method. So let me visualize that for you. So what I first do is I start with inverse propensities. I'm still using the same inverse propensities of IPS. But instead of trying to estimate the reward, I want to estimate the error of the direct method. So what I can do is I can, for each interaction, I can look at what is the interaction that I would have predicted with my regression model versus the actual interaction. So if I see a click and the regression model also predicted a high probability of a click, this is going to be a very small value. If I see a click and it predicted no click, it's going to be a high value. Vice versa, if I don't see a click and we predicted a click, it's going to be a high error, etc. And of course, we have to match this back to the new policy. So what I'm estimating on this slide is not the reward. I'm estimating the error of the direct method. And the key feature here is, if we combine that with the direct method, we have an unbiased estimator again. And as you'll see, it could reduce our variance. So what do we have here? So the direct method starts with, the doubly robust method starts with the direct method. So that's what we think performance is based just on our regression model. Then we get an IPS estimator, but inside the IPS estimator, I'm not just using the click, I'm subtracting the predicted click probability in this case. So the predicted interaction probability. And we can prove that this is unbiased, basically because the predicted click is going to, in expectation, negate the effect of the direct method, and then we are left with an IPS estimator, which is already unbiased. A different way of formulating this, so this isn't very common, but it's going to be useful in the learning strength scenario, is that we have the direct method plus the IPS estimator minus a covariate. And the covariate here is going to cancel out the effect of the direct method in expectation. All right, so key here is we start with the direct method, which is based on our regression model, and then I use IPS estimation to correct for the error of the direct method in expectation. It's called doubly robust because it's easier to be unbiased with this estimator. For each item, so for each item that's individual item, we either need the inverse propensity to be correct, so we know this ratio between the two propensities, or the regression estimate to be correct. So either this value over here has to be correct, or this value here. And this can vary. So for some methods, you can be correct with regression, and for other items, you can be correct with the propensity. And then you're unbiased. So this is unbiased whenever either IPS or the direct method is unbiased, but also in other cases. That's why we call it doubly robust. Importantly, if you have a high covariance between the covariate and the IPS estimator, you can prove that you have decreased the variance. So that we see in the bottom, the variance of this estimator is basically the variance of IPS plus the variance of the covariance minus twice the covariance between the two. I realize that by calling it covariance, I'm making this sentence harder than it should be, but you can see from the equation what I mean. So this, so far, is things you might have seen in standard sort of reinforcement or bandit literature. So this is not specific for ranking. But the reason I've went through this is because I want to show you sort of this basic overview, right? So we started with IPS, where we reweigh observations according to logging policy probabilities. It's unbiased if the propensities are correct, but we could have very high variance. So high variance is usually a problem here. Then I showed you the direct method, where we purely use regression estimates. So we only use regression estimates, which means it's almost certainly biased because your regression is probably not 100% correct, but you have extremely low variance because you're ignoring all of your interactions, right? So the other extreme end. And then we have the doubly robust method, or the doubly robust estimation, I should say, which is tries to marry the two. It starts with the direct method and then uses IPS to correct the bias of the direct method. It has much easier unbiased criteria, so it's much easier to have an unbiased doubly robust estimator than to be unbiased in the other cases. And we can have a lower variance than IPS if regression is decent. So it's trying to get the best of both worlds. Now, a bit of foreshadowing. We're about to look at learning to rank. And if you're familiar with sort of the unbiased learning to rank field, then you know that you've probably seen that basically the state-of-the-art work is stuck here at the top in IPS estimation. There are some methods that are doing actually the direct method, but they don't call it that. But most of the work is on IPS, and practically none of the work is in doubly robust estimation. So the question I wish to answer for you today is, why is that so? Like, why didn't we see doubly robust estimation before? And how can we actually get doubly robust estimation in the learning to rank setting? All right, so this is what it looks outside the field. Up until before this work, it mainly in learning to rank, we mainly had the top version only. So that's part one. Sorry for, I mean, it was a very quick overview. I hope that you could follow it somewhat. Luckily, I'm going to go over most of these methods now again, but in a different setting. So that should bring everyone up to speed, hopefully. All right, so in counterfactual learning to rank. So the biggest problem for an audience like this, I probably don't have to explain this, but I will anyway, is that the ranking setting, we're not showing a single item, we're showing an ordered list of items, like a ranking. So visualize here as we could show 3 items at once. So we select which 3 items and in which order to show them. For this talk, the goal is still to maximize the number of interactions, but now the interactions can happen with any of these items, right? As you know, search engines, recommendation systems, most of them use something like this in their foundation. And what is the first thing that you run into? What sort of characterizes the ranking problem? It's this combinatorial thing, right? Like, it's the number of rankings is so enormous that it really makes a lot of approaches unworkable. So I've been working with the ranking for almost 8 years, I think, 7.5 years or so. This still blows my mind every time. But the number of top 5 rankings, so the number of top 5 rankings that you could make, if you want to have, with only 20 different items, you already have more than 1 million different top 5 rankings that you can make. If you want to go to 100 million, you need 42, and then you're already over 100 million different possible rankings. I know this, right? But every time I see the graph, I kind of get a mini heart attack because it's ridiculously fast how quickly it grows. Why am I bringing this up? If you remember, the IPS and the doubly robust estimation used propensities, which was the probability that an action took place. If we say that each ranking is an action, then we know that these probabilities are going to be minuscule, right? So if there are 100 million possible actions and you have to divide a probability space over all those actions, there's going to certainly be at least one action that has a probability lower than 1 in 100 million. Now, I said that variance, it becomes a problem with tiny propensities. This is like the most extreme version of that you can get. So normal counterfactual estimation doesn't work when you apply it to ranking because of this enormous action space problem. So we need something else. And this is what we get in the counterfactual learning to rank field, because it focuses on, instead of focusing on the selection bias from the logging policy, we focus more on correcting for position bias, and we have specific methods for ranking. So I'll now introduce sort of the state of the art here up until, well, let's say February. To start with position bias, right? So I think we already heard some work on position bias today. The main definition I'll be using is that people don't look at all of the items there are on a page. So here's an eye tracking study for people looking for airport parking. And what we can see is that red block up here shows us 100% of people. So everyone who looked at this result page looked at the top 2 results. So if you're on top of the ranking, pretty much everyone is going to take a look at your link. If we go to result number 8, so here at the bottom of the ranking, we have less than 50% of people are still looking. So that basically means that if we, beforehand, if we think about the click-through rate, without knowing anything that's on these links, we already know the click-through rate is not going to be higher than 50% just by being at the bottom of the web page. Right, so that's how strong the effective position is. And this is a bias because you can average this over 1 million users. It stays this way, right? So it's a problem with the expected value. This is not noise. So to deal with position bias, the high-level approach is to get a mathematical model that gives us a relation between clicks and the quality of an item. So I'll just use the word relevance here, because for ECR that makes more sense. If we have a mathematical formula that gives us the relation and it's invertible, we can usually work our way to a method that can correct for it. So for this work, I will use the following equation. So here we have the probability of a click on an item D. So you can think of D as a document. Position K, so that's the rank at which we are displaying an item, is well, and then here on the right, we have the probability of R. I'm going to use R as the relevance. So how likely an item is relevant. And then I'll call these the bias parameters. So these are specific to the rank. So on the right here, we have what I call the trust factor. This is based off what's sometimes called trust bias. That's the number of people that are going to click at a rank just because they trust the search system. So if you are #1 on Google or Bing or Yahoo or something like that, there's a lot of people that will click on that result, no matter what the result is, because they trust the search engine knows better than them. So we capture that with this beta parameter. And this varies per rank, right? And then the alpha parameter tells me if an item is more relevant, how many more clicks do I expect? So if an item is, if I compare an item at the same rank that's completely irrelevant and 100% relevant, how many more clicks would I expect at that rank? So it can capture, for instance, the examination that we've seen on the previous slide, the examination probabilities, but it can also capture some more patterns. So it's more expressed than the earlier position bias models. And importantly, we can invert this, right? So if I want the probability of relevance, but I have the probability of a click and I have beta and alpha, I can just extract beta and divide by alpha, and we are in the relevance space. So traditionally, people work the beta side of this. And what that basically looked like, if we're correcting click-through rates, if we have a click-through rate at the top of a ranking, so here we have item A, we can say, well, we probably don't have to do anything because 100% of people already looked at this item. But if we take item H here, which is the 8th item, where 40% of people look at that rank, then what we could do is we could take the click-through rate and multiply it by 2.5, because that would give us the click-through rate as if 100% of people looked at it, right? So if I see a click-through rate of 10% down there, then I'm going to assume that the click-through rate would be 25% if everyone were to look at that position. So this is basically the idea from about 2016 and 2017 in counterfactual learning to rank. And if we write that to an IPS estimator, the propensities now become the expected correlation. So I'll call that exposure. So we ask based on the logging policy, right? So I'm sampling the rank here from the logging policy. What is the correlation that I expect between clicks and relevance under the logging policy? That's basically this equation. It's just an expectation over the ranks and the correlation at each rank. So this tells me if an item is more relevant under this logging policy, how many more clicks would I expect? And then our IPS estimator looks very similar to before, but it has some trust bias corrections as well. So we take if we wanted to know the relevance of an item, I'm going to sum over n observations. For each of these observations, the click is going to tell me whether it was a click or not. I subtract the beta parameter for that rank, because these are the clicks that we get for free on that rank. And then I divide it by the propensity to move from the click space to the relevance space. The advantage here is that because propensities are now based on exposure, we're avoiding this combinatorial problem. So these propensities can still have a decently high. We're not talking 1 in a million here. They can be high enough that we avoid the variance problem, and it can still be unbiased if our model of clicks is correct, of course. However, the downside is that now I need to know the alpha and beta parameters as well. So we need to know something more about the way that users interact with our rankings. But if we do, we can now apply IPS estimation. So this is more or less what's been happening in counterfactual learning to rank for the last 5 years or so, 4 or 5 years. For my introduction, you are probably asking, okay, why aren't we seeing doubly robust estimation or the direct method here? That's a hard question to answer, right? Because I don't know, I can't do a counterfactual on the history of the field. We can't pinpoint the exact reason, but my guess is that if you think about the direct method, we needed to know the value that we're estimating, which is here the relevance R. And for doubly robust estimation, we need to know the error of our regression. So we need to know, in this case, the difference between our predicted relevance and our true relevance. The problem is we never observe relevance. We only observe clicks. So there's never a point where we can say, this is how far off my regression was directly, right? Like, because we never see the relevance directly. That means that you can't take an existing doubly robust estimator, replace the propensity with exposure, and then it works. So I think this is why it took so long before we move out of IPS. And let me show you how to get out of it, right? So the first step is the direct method. So luckily, there's already other people who realize that, oh, you can actually, for instance, get an unbiased estimate of a cross-entropy loss based on relevance using clicks. So what's happening here, right? In a binary cross-entropy log, you would have the probability of R over here multiplied by log of the predicted R. Well, the IPS estimate gives us an unbiased estimate of R. So what we have over here is the same IPS estimator as before. Then what we need still is on the right here, we need the probability of 1 minus the true relevance multiplied by a log 1 minus the predicted relevance. Now, luckily, there are some tricks that you can use to get that negative as well. You could do 1 minus the IPS estimate. I introduce a variant here that's, in my opinion, slightly better, but it's the same idea. And this way we can get regression of relevance based on clicks, right? So we can unbias the estimate, the cross-entropy loss. We can optimize that to get an estimator that's probably pretty close to the true relevance, but it's not going to be perfect, obviously. So, all right, so we can solve this basically. Other people have already done most of the work here. The insight that I had, that I think made the next step possible, is that if we formulate the doubly robust estimator with this decomposition that I used before, if you remember, the doubly robust estimator is the direct method plus the IPS estimator minus a covariate. It now looks much easier because all that we need is a covariate, and then we are done, right? So from this equation, we're only missing the last part. The question now turns into, can we think of a covariate? And then we have a doubly robust estimator. If you recall, what we need from the covariate is we need the same expected value as the direct method, because in expectation, they have to cancel out. But we want a very high covariance with IPS. So this is what I propose. Let me explain what's happening here. So again, we're averaging over n observations. The nominator here is the correlation that we see according to the ranks at which items were displayed. So if an item was displayed at a position where they can't be observed, for instance, alpha would be 0, it wouldn't do anything. If it was displayed at the top of the ranking, this would be a high value. The denominator here is the expected exposure, so the expected correlation. So this is according to the logging policy what we would expect. So basically what this thing is doing here is it's saying, in the data that we have, does this item get more or less exposure than what we expect according to the logging policy? So was this, let's say, a lucky item that it got more exposure than we would expect, or was it an unlucky item that got less exposure than we would expect? If you calculate the expected value here, we see it's unbiased, because if you recall, rho, the propensity was just the expected alpha value. So this kind of trivially cancels out to just giving you the direct method. All right, so seems quite straightforward, but actually, if you put it all together, something really nice happens that I didn't expect until I wrote it down, actually. What we see is if we put it all together, if we write it out, is we start again with the direct method, then we have our IPS estimator, right? So up to here, it's all the same. But now inside the brackets here, what we have is we have the observed interaction, so whether there was a click or not, minus alpha times the predicted relevance minus beta according to the rank at which it's displayed, which is basically the predicted click probability. So we look at the rank at which the item was displayed. We look at, do we predict a click here or not, according to our regression model? And did we see a click or not? And we take that difference, and then by reweighing it with the propensity, we get an unbiased estimate. So basically, we look at the error in the click probability, and by reweighing it with the inverse propensity, we bring it back to the relevance space. And as you can expect, if our relevance estimate is very good, if alpha and beta are correct, there's going to be a high covariance here. The second part of this equation is basically not going to do very much, which is what we want, right? So we still need alpha and beta to be accurate. Like, I can't get around the fact that we do need to know the user behavior somewhat. We do need these bias parameters, but to be unbiased, we only need for each item either to know the logging policy propensity, so how likely is the logging policy to display the item at a certain rank, or have an accurate regression estimate. So this thing over here basically needs to be correct, and then we are unbiased. To my knowledge, this is the first doubly robust estimator that doesn't require us to directly observe the error. So we don't actually see the error in what we're estimating because we're working with the clicks instead. And we can actually prove that if our relevance estimate is between 0 and twice the actual relevance of an item, then we are less biased and have less variance than IPS. So that doesn't mean that if we don't have this, that we are more biased, but this is where we can prove it, basically, right? So, so that's a very nice feature to have. There are some caveats, but for the sake of time, it's not very important. I want to skip over it, and I want to give you some intuition of what this is doing. So this is not 100% accurate, right? I want to give you sort of an idea how to think about it. So the real way to think about it is this equation, right? Like, this is the actual thing. But to sort of understand in your head what's going on, I think a good way of thinking about it is that if you use IPS and you have your data, so here there are 4 items that were never displayed during logging, right? So when we were logging data, these were just never shown to users in the top 4 in this case. So if we use IPS, we know that their estimates are going to be 0, because if there's no clicks, the IPS estimator just assumes nothing, right? So this, so we know that if whatever comes out of it, it's going to be a re-ranking of the items that were shown, in this case, the top 4. So we can never expect one of these bottom items to go up, which seems unfair, right? Because it's just because these items weren't displayed. So this is a cause for variance, actually. If we think of the direct method, we don't have this problem, right? The direct method can move everything around based on what the regression model is saying. However, we are ignoring any sort of interactions. So we don't know whether we're actually following interactions. The doubly robust method, you can think of it as doing this. Again, it's not like this is the nutshell version, right? So intuitively, you can think about this. It's not 100% mathematically correct, of course. But the way that I think you can think about it is we start with the regression model. It starts to re-rank everything, right? Because it can give us an estimate for all items. Then we get this sort of intermediate ranking, and then we use our interactions to then correct that ranking again. So we first we rank based on our regression model, and then we use our interactions to update that once more. So this, you can think about it. Of course, if you actually work with it, please look at the formulas. But this is how I would think about what's going on. All right. That's theory so far. Of course, we want to see it in action. We want to know what it actually makes a difference. So the way that that I've evaluated this is based on simulations. That's really the only way that you can do these evaluations properly. We use commercial search engine data sets, and then clicks are simulated based on the relevant judgments in there, but we add a lot of position bias and noise, of course. Let me start with, this is a setting where there's a top 5 ranking, so only 5 items can be shown at once. And the bias is unknown. So the method has to first estimate the bias, and then correct for it. So the alpha beta parameters are not known. This is what it looks like. So let's first explain the axis, right? So here on the y-axis, we have the expected number of clicks on relevant items. So how many times does someone expected to click on something and think it's relevant? The higher, the better. This is our metric, right? The x-axis is the number of queries in the data set. So if I vary the amount of data that we have, and this is on an exponential scale. So we're going all the way from 100 to a billion here. Then the straight line down here is the logging policy performance. So this is the performance of the system that we use to gather data. And the line up here is the best possible performance that you can get. In a simulation, we know this because we know the relevance labels, so we can just do learning to rank on the relevance labels. And this green line here is inverse propensity scoring. So most previous work would be relying on a method like this. And as you can see, it is unbiased, right? It's provenly unbiased here, assuming the bias is correctly estimated, which I think it pretty much was at this point. But you see that a billion observations, a billion queries in the data set is not enough to get to optimal performance. This must mean that it's a variance problem, right? Because we can, in a different setting, it did know the bias where we can prove it's unbiased, it still had this problem. So we know that this is variance here. Then the blue line here is the direct method, and you can see that it works much better in this setting. I think this is because it can re-rank items that are never displayed in a top 5 set, in one of the top 5 rankings during logging. And then we have this red line here, that's a doubly robust method, which does even better. This difference is significant. I measured it at a million queries, so over here it's significant, and from there onwards, as you can see at the start, it's pretty much the same. But it's a meaningful difference. If we compare it here with inverse propensity scoring, that's where the crazy part comes in, right? We see the performance that we need, that IPS has at a billion data points, is a performance that the doubly robust method has around 200,000 data points. So that's a data increase of more than 1,000 times more efficient. So that's not something that you normally expect to get from your experiments, but that's what came out of this. So basically what it's doing here is by using sort of combining the direct method and the IPS estimator, it can do better than both. And that means we need a lot less data here. I don't think I mentioned the direct method here has no prior knowledge, so it's only trained on the data that we see here. So it's not that these methods are cheating by using more information. So they're applied under the same exact circumstances. Here's a different data set, MSLR. We see pretty much the same pattern. This one I find very interesting. This is the Stella data set, because here IPS and the direct method perform about the same, right? So performance-wise, using IPS or using your regression model doesn't seem to make much of a difference. If you start combining them, however, you do get a big increase again. And again, this is we have a factor 1,000 or so increase here. I also looked at a full ranking setting. So here all items can be shown at once. In that setting, IPS actually does get optimal performance after about 100 million queries. But initially the direct method is better, but it can't converge at the right place. So it has this bias problem here that I told you about before. If the regression model isn't perfect, you don't have this perfect convergence. Interestingly, the doubly robust estimator combines the best of both worlds, right? Initially, it follows the direct method, but it converges like the IPS method. And depends on the data set whether that pattern survives, but it's always sort of the best choice. I just briefly want to mention, I also tested a session where we intentionally put the incorrect bias in these models, so to see what happens if it doesn't know the bias at all. Those are those stripe lines you see over here. The main point is the doubly robust method is still significantly better than the others. So even when your bias estimate is completely wrong, it's still better to use it than the other two. All right. With that, I want to conclude. So what I would like you to take away from my presentation here today is, right, position bias is a very important problem when you're dealing with interactions with rankings, and it will disrupt your optimization if you don't deal with it. The existing solution up to a couple months ago, let's say, was mainly to rely on inverse propensity scoring based on exposure. what I've contributed in this paper, at least, is an exposure-based doubly robust estimation method for learning to rank. So I think this is the first doubly robust method that is really built for exposure or position bias.
الو محمد انت موجود في بيته.
Okay. Somebody's oh, there we go. So we have less bias and variance with decent regression. Basically, we can prove this. And in the experimental results, a really big difference. So in top 5 settings, you may need 1,000 times less data to get the same performance as IPS, which I don't have to tell you, but this could make a very large difference, obviously. So could mean that we're opens a whole world of possibilities or applications basically there. So we now, to wrap it up to the start, right? What this basically means, I think, is that we now have state-of-the-art counterfactual estimation for counterfactual learning to rank. So if you remember at the start where we had these 3 different methods, they're all now also applicable for counterfactual learning to rank. Here again, this is the paper it's based on. Thank you very much for your attention.